Welcome to the Abstract Synthesis Podcast, where we go beyond the paper abstract to synthesize new ideas in the world of program synthesis and symbolic AI. Brought to you by AGI Research Lab and DIA, I'm your host, Brian Landers. This is a special episode featuring live interviews from NeurIPS 2025 in San Diego, California. Here we are at NeurIPS 2025, and I found my teammate Clément Bonnet.
Clem, yeah.
This is Clem from the NDIA team. What are you looking forward to seeing here, Clem?
Yeah, the week has been very intense, very packed. A lot of interesting posters and orals and talks, good keynotes in the world of neuro-symbolic AI and program synthesis.
You yourself,
and reasoning as well.
You had a poster, right?
Yeah, I had a poster on Wednesday morning, 3 hours and a half of intense talking. Very fun, very very nice with Matthew McFarlane. And today I was heading to the embodied world models workshop. A lot of interesting things about like modeling the world and modeling situations that agents are in. There's also a nice workshop around causality, how to build like causal models of the world. So
very exciting.
Looking forward to these two at least.
Do you want to weigh in on, do LLMs have world models?
I'm a little bit contrarian on that side, but I believe, so I've heard from, I'm just quoting somebody else, I forgot who, but they were saying that LLMs could be kind of marginalized world models. So they don't have, they don't model like the next token given a specific action. So they don't model like transitions to a next state given a specific action, but they kind of marginalize, so they sum over all possible actions, all possible latent causes of the world to predict the next state, to do some reasoning. So in that sense, they could be like marginalized world model.
Okay.
It would be very nice to make them actual world models. Yeah, explicitly model causes instead of implicitly model them, basically.
This makes sense.
Does that make sense?
Yeah.
It's a bit of a contrarian take, but...
That's really cool. I'm happy to hear contrarian takes. Hot takes at NeurIPS.
Yeah, there's also a very nice workshop on efficient reasoning today. I assume it's going to be packed as well with like all the reasoning folks.
Excellent. All right, did you also see program synthesis is the topic of the podcast? You saw a presentation last week on I think the one paper that had program synthesis in the title. How was that? Was that a good poster session?
Yeah, there's the POE world from top. Amazing paper. I went to the poster. A great guy. Amazing work on mixing like LLM program synthesis as well as turning it into a probabilistic world model. So super useful for decision making. There's also this great paper, NeurIPS PR, maybe we'll hear some of these papers in the podcast. Looking forward to it.
All right, Clem, enjoy the rest of the day. Thanks for jumping in.
Yeah, thanks so much, Brian.
Can you please introduce yourself?
Yeah, hi, I'm Antonia Wüst. I'm a PhD student from TU Darmstadt, and my research focuses on abstract visual reasoning and concept induction, and specifically for that I'm interested in program synthesis and neuro-symbolic AI in general to solve these challenging problems.
This is super exciting. Okay, neuro-symbolic AI. Does that fit kind of within the program synthesis world? How do you see it?
Yeah, I mean it can have various forms, of course, but how I like to see it is that to understand something about our data or our problems that we have at hand, sometimes it can be beneficial to have some neural component that tells us more about what we see, for example, in images, and then the reasoning part on top of it, I usually prefer to use symbolic methods for that, or think that it's really beneficial to like maybe take some steps back and don't just throw an LLM at everything, but use symbolic methods that actually can reason faithfully about the content or the information we have at hand.
Yeah, it's like a very powerful tool that we have at our disposal, right?
Yeah.
So why not make use of it? Yeah. Doesn't have to be, everything has to be an LLM, right?
Yeah.
Okay, your work focuses, I think, a lot on vision and sort of like visual perception, I guess you could say.
Yeah.
How did you choose that? Like, why did you end up kind of there? You know, it could be anywhere in the field and you ended up kind of focusing on that. Why did you do that?
Those are the problems I'm very excited about, because I feel like for us humans, we have like a really good understanding of visual content and can abstract and extract the important information quite quickly.
Yeah.
And I'm quite fascinated by that and would like to understand better how AI systems could come closer to that human analogy making and quick like clustering and understanding of visual content.
Yes, seems incredibly valuable. So tell me about any of your projects that are kind of based in this field, especially related to program synthesis. Does anything come to mind?
Yeah. My recent project is looking at visual concept induction. So we try to figure out visual concepts just by having positive and negative examples of this visual concept. So this concept can be anything. We mostly focus on real-world concept in that work. So, for example, there's a scene and you see a cake and birthday candles on that cake. And so you have a few image examples of that, but also you have some examples where you just have a cake or just have candles. And the goal is to figure out, okay, what is it that the positive image examples have in common? And for us humans, I feel like this is quite an easy task, just from a few examples to understand what is like the underlying rule that separates these images. But we saw when we give these kind of tasks to vision language models, so kind of the new great architectures at the moment, these are really bad at inducing rules from image examples. I think challenging part of it is that you present multiple images at once, but also I feel like the reasoning about these different informations is still a bit fragile, I would say, so not as faithful.
Do you mean versus like text kind of based data or something like that? Like the visual data is kind of different for models?
But I personally still feel also that pure text-based reasoning also still has its flaws. I think we are further there than we are in vision, but I think vision is probably especially hard again because you have to first extract something from the visual content, and then you have it kind of in a text domain, and then you have to reason about it in text. So I think we can do better at that, I guess.
Yeah, I think you have a workshop you're presenting at tomorrow.
Yeah, exactly. I'm at the multimodal algorithmic reasoning workshop, and I present our work there, which is where we try to combine vision language models with program synthesis.
No way! That's so cool.
So that we get the best of both worlds. That we get the perceptual information and leverage the vision language model to just give us information about what we see in the image, but for the reasoning part we use programs. So we want to find a program that can explain to us like that there is a cake and candles in the image and not just the vision language model itself.
That is super cool and super relevant to our focus with the podcast, so I love hearing that. Yeah. Is it a paper that you're presenting or a project you're working on? What exactly are you presenting?
It's a paper, yeah. We submitted it to the workshop, but we have extended it now as well, so the full paper is also available on archive.
Super cool. I would definitely link to that in our show notes. Yeah. The program synthesis side, was that something you had studied in school? Where did that come from? I kind of get the model side and even the image kind of focus. It's like a wonderful way to look at the world. As you said, human perception is so much based on visual perception. But why program synthesis?
It actually started with my master thesis. So when I knew I liked AI a lot, but I didn't really know in which direction I wanted to go back then. But when I applied for my master thesis, my supervisor was proposing some possible topics we could work on. And then one of the works he proposed was trying to combine the Dreamcoder paper with visual concepts. Okay. And somehow that sounded really cool to me. I also like the Dreamcoder paper a lot. And so that's when we started to work on trying to combine program induction with visual concepts.
So we're at NeurIPS. You've got your workshop, but there's a lot of other time you're exploring. Have you seen anything cool? What are you looking forward to while you're here in San Diego?
Yeah, the thing I like about NeurIPS the most is I think connecting with the community, because I feel like here's the focus on program synthesis and neuro-symbolic AI is quite more big than maybe at ICML or something. So I had some nice talks with some researchers that also work in that area, and I usually take a lot from these talks. And
have you seen an uptick in the sort of symbolic side, or is it just is it mostly deep learning and LLMs?
I think there's a niche that focuses on that, but I feel like the general direction is more towards we just need better data and scale and so on, which I'm not a super fan of, but it's nice that you still find people that also focus on the neuro-symbolic AI and also interpretability side of things that comes with it. Yeah.
Are you yourself a fan of kind of cognitive science? A lot of people who get into neuro-symbolic work love the human brain, sort of figuring out, what is this connection between human intelligence and reasoning, and how do we get to AGI? Are you a fan of this kind of topic?
Yeah, I'm a super fan of cognitive science. Unfortunately, I never studied it, but every time I see cognitive science papers, I find something very interesting or interesting aspects that relate also to my work. So I always enjoy talking to cognitive scientists as well.
Yeah, me too. It's very fun. Thank you, Antonia, so much for speaking with us. We look forward to checking out your paper, but thank you so much for your time.
Yeah, thank you a lot.
Hi, I'm Leopoldo Sarra. I have a background in physics, and I'm working on machine learning applications for science. And I'm generally interested in how can we make new discoveries in physics and science more in general. And program synthesis is one way of doing this in an interpretable way and verifiable for the scientists.
Yeah, absolutely. It makes sense. And you work specifically, or at least partially, within quantum, like quantum chips, quantum thermal dynamics. Is that right?
Yeah, exactly. Like quantum physics is sort of counterintuitive. And the idea is, can we have some program and some algorithm that can help us figure out how it works? And this is why I've been exploring program synthesis in applications for quantum computing and seeing how it can help us, for example, decompose circuits and express them into the gates that are usable for computation on real hardware, for example, or other ways of finding high-level components that we can reuse. And so we express them as programs. Mm-hmm. And by using the architecture and the frameworks of program synthesis, we can find the solutions and then express them back into gates.
Do you actually work with hardware, like quantum hardware? Does it exist? Are you building that, or is it sort of more theoretical still?
So I've been working mainly on the theoretical side, so showing what you could do. In the latest paper I've been working on, reinforcement learning with gadgets for quantum computing.
With gadgets?
Gadgets are this high-level sequence of gates that we can extract with program synthesis that can reduce the length of the search for your decomposition of the circuit. And essentially, we can simulate them. There are platforms that allow us to simulate them. Okay. And also on real hardware, or you just run the simulation that emulates some of these quantum devices. And essentially, we choose the base, so the set of gates that you can do in your real quantum computer. Yeah. And so we can decompose a circuit using program synthesis into exactly the set of gates that you can use in your quantum hardware.
That's very cool. So you work at Axiomatic AI, is that right?
Yeah, this is something I've been working recently. Like 1 year ago, I moved there. And we're exploring also how can you do formal verification for essentially engineering pipelines. And one way that we're exploring is theorem proving and program synthesis in a way that is interpretable. I've been working on quantum system, but in this new endeavor, I'm working more on photonics surface, essentially.
Very cool. How did you get into program synthesis and sort of symbolic work and verification? It's a very particular kind of field within AI to get interested in. How did you find it?
Yeah, so this started during my PhD actually, so a few years ago. We organized a workshop called Artificial Scientific Discovery. So how do you use machine learning for making new discoveries, right? And there are many black box techniques. And there was one paper in particular called Dreamcoder.
Dreamcoder?
Yeah.
Like Kevin Ellis?
Exactly, yeah. And he was showing how you can create concepts by doing this program synthesis algorithm, right? Yes. And enumeration, right? And then dreaming, and then
yeah, it's a really cool concept.
Yeah, and he was showing some examples also for symbolic regression, right? So finding equations from just data and extracting them by using this program synthesis algorithm. And from there we thought, okay, so program synthesis is not just about writing programs, but could be applied also in other settings.
Yes.
And from there, the idea of let's try to apply this to physics. So we got in contact with Kevin, and I've been working with him for these projects. The initial idea was sort of ambitious, can we write new quantum algorithms?
Wow.
Right? And this is hard because we don't have many examples.
No.
Right? And
no, this is new territory.
Yeah, it's brand new.
You said new science. That's what attracted you to it.
Yeah,
makes sense.
Exactly, right? Imagine we could discover a new setting where a quantum algorithm performs better than a classical one.
Right.
It could be
That's exciting,
right? Because sometimes it's counterintuitive. So for humans, it's very hard to design quantum algorithms.
Yes.
While a program that is trained on these things could understand the logic in some sense and find new. But this is too hard. They don't have enough samples, and each one is a different class.
Okay. Very challenging problem.
And from there, so we said, okay, let's simplify.
So you said, back it down. That's a little too hard.
Yeah, exactly. Okay, slow down. We just have a semester. Let's do things simpler. And then we said, okay, let's perhaps think of like decomposition. So the so-called transpilation. So the process from where you have your algorithm expressed, like in quantum computing, you call it a unitary matrix. So it's the transformation that maps your input gate to the output gate, right? So essentially tells you what the algorithm should be doing.
Okay.
And trying to think, okay, we cannot implement this unitary. We need to decompose to the elements that we can actually apply to our surface.
Yep.
Right? On the hardware that we have.
Yep.
And so we started thinking, okay, there are algorithms to do this, but you need to code them yourself.
Yes.
So you have a different set of gates. There are different algorithms that tells you, okay, we can decompose it with this kind of complexity, and it may not even be optimal. So it's a very hard problem. And we thought, okay, let's try to use program synthesis perhaps to work on this and see if we can make something that works better.
And that's what you picked. Did you have success in sort of studying that?
Yeah,
Not that success even is the end goal. Like exploration is worthy kind of in and of itself. But what happened? Like I got to know.
Yeah. So we started thinking, okay, how do we frame this problem, right? And how do we compare? And so we said, okay, let's simplify yet again the problem. And we said, let's imagine we know the solution, like we know which are the high-level gates, right? But we don't tell our algorithm, right? And so we give our algorithms like the matrix that we want to decompose, and we give that just the unitary gates that we can use. And then we said, okay, figure out what's the best way to express that. And so what we saw is that it was able to find the gates that we would have used, like the high-level gates that we.
And that was kind of like, okay, something cool is happening here.
Yeah, like it's like, okay, it's learning, right? It's sort of understanding that if you use these gates, the description length is shorter, right? So you minimize the description length, you're finding the right way to describe the system. And
that's
so
very
this is
cool.
the program that you're learning.
So that's how that was like your entryway into this.
Yeah, right. So we simplified the dream coder. We said, okay, let's make something simpler. We cannot generate the samples. Like it's harder to do the dreaming part in that case because there was an overlap in the data sets, right? So it became too. It would be like you would learn just the distribution that we're telling. Right. So what we said is just sort of enumeration compression. So try to enumerate a lot of circuits and then try to find the best abstraction that compresses them. And this is the program that we're using. And we're still using like lambda calculus and expressing all the circuits like as programs. Where the programs would mean actually in this case, which gate do you put on the circuit?
This is so cool. What do you think is the future of quantum computing? Like I think we were chatting a little bit before we started recording about use cases for quantum. It's not always the same thing as what's appropriate for kind of current computing standards. Where do you think this goes? Dream for us.
There's a lot to discover more, like to think about. I think for sure, like simulation and quantum systems, right? You can simulate with quantum computers. So it seems sort of like a great tool to explore the quantum world, right? And also we know it's a stronger model of computation in some sense, so it's possible that we will find more algorithms that can be more efficient to use in quantum. The main problems we had is that you need to encode your data also as quantum states. And this is sort of the expensive part that many times makes you lose most of the advantage.
Yeah, that sounds like a really hard challenge.
And there's some more work to do, but there's also a lot of investments, and so this will become like quite feasible in the next decades.
Thank you so much for taking time out of your NeurIPS 2025 to chat with us in the hallway. We really appreciate it.
Thank you so much for inviting.
Hi, my name is Top. I'm currently a PhD student at Cornell, advised by Kevin Ellis. Do I say what I work on too?
Yeah, please tell us. What are you working on? Unless you can't say, is it stealthy? Is it like?
Well, very broadly, I'm interested in kind of like more human-like AI, human-like learning. And more recently, I've been focusing on world modeling, specifically symbolic world modeling.
This is a huge hot topic, this world model stuff. You actually presented a paper over the week of NeurIPS, right? So what was your paper called?
It's called PoE World, but I don't remember the full title. I think it's complex.
I was wondering about this, if paper authors, because when I interview paper authors, I read the whole thing and I'm like, that is a mouthful.
Yeah.
It's good to hear. Thank you.
Yeah.
You've validated something that I wondered about.
Yeah.
But anyway, it's
But
about.
kill you won't.
Yep. Everyone needs to go check out your landing page
Yeah.
for the paper, because it's got this wonderful like video game, kind of video that people can watch the AI playing against. What is it? Montezuma's Revenge.
Yeah. Thank you.
It's really cool. How was the reception for your presentation, by the way?
Well, I think it's good. A lot of people show up, and a lot of people seem to like it. I think usually the first question people would have is like, well, are we dealing directly with pixels? And then I have to kind of set their expectations straight that, we're doing symbolic world modeling, so we're just gonna assume that our input is also symbolic.
Okay.
But it's, for future direction, eventually we want to relax that assumption. Have something that goes from, deal with pixels and then reason with symbols and, all this different levels of abstractions. Eventually we'll try to get there, but for this work, the input is going to be symbolic.
By the way, you mentioned Kevin Ellis earlier. Other folks that I've interviewed on this, for NeurIPS 2025 mentioned Kevin Ellis as inspiration for their work, specifically Dreamcoder.
Yeah.
Is that how you found Kevin Ellis too?
Not exactly. So I first got into Cornell, and I wasn't directly admitted by Kevin Ellis. I was admitted by a different professor, and then I just started looking around for professors who I could potentially work with at Cornell. Nice. And then I found out about Kevin Ellis and Dreamcoder. I thought it was super cool, and then eventually I got to work with them.
That's super cool. Do you work yourself at all with ArcAGI, the benchmark?
I did at some point, and it was so hard that I gave up.
We hear this.
That was my first year PhD rotation project with Kevin.
Okay.
It didn't lead too much. And eventually we gave up. And then I know eventually OurLab, but I wasn't involved in it, but eventually OurLab did make some progress on it, and we did win the first ARC Prize paper award.
Yeah, totally. How did you get into, program synthesis related work? I mean, it sounds like you work kind of, do you think your work covers program synthesis at all?
Yeah, to some extent. During undergrad, I was pretty much working on few-shot learning. I think back then around 2020, few-shot learning was big for image classification.
Yeah.
And so a lot of people were really trying to think about how do we really just with just maybe 5 training images.
Yes.
How do you learn so quickly from so very little data?
Yeah, that's the question right there. Yep.
But I think at that point, then after that, around 2021, maybe a lot of foundation models come out.
Yep.
And people just sort of gave up on few-shot learning. They just okay, we have these big models and it can do everything, so we just don't have to do all these new algorithmic thing for few-shot learning anymore.
Interesting.
But I'm always interested in this, how can we learn more, as efficiently as humans?
Yeah.
And it turns out that if you have symbolic structure, programmatic structure, you might be able to be at the human level on many kind of reasoning tasks.
How did you choose, to kind of dive into this world model stuff, which I think is super relevant to AGI and folks trying to bridge the gap between where we are today with AI and human level intelligence, like you were talking about.
Yeah.
Why did you get into world models?
So I think initially I just kind of started thinking about how to make machines learn more like humans. At first I was kind of working on very toy domain where we're just trying to say figure out a rule. So that's kind of called concept learning.
Yep.
So we've looked more into how do you actively learn a rule.
Okay.
In the same way that with human child, we just kind of come up with hypotheses and then go out and experiment in the real world and then revise your hypotheses.
Yeah.
So we just kind of start with that. We work, initially we work with this domain called Sendo, which is kind of a lot like Blickit detector by Alison Gopnik group, but kind of more, it's a more advanced version. So we kind of look at that. It's this board game where you pretty much trying to figure out what's the rule that governs the game, something like that.
Kind of a meta thing, yeah.
Just mostly concept learning.
Okay.
But yeah, so we just kind of start from that, and at first we were looking into okay, how do you do active learning and this kind of stuff. That is cool. We in concept learning, we have a good way of thinking about active learning through a Bayesian inference kind of view, and One way that you can do active learning is through maximizing expected information gain and everything. But then we found out that to make this work in the real world, the part that's really hard is the part where you come up with hypotheses. So how do you induce hypotheses?
Yeah.
And hypotheses about POMDP, like a kind of like a RL domain, RL environment,
Okay.
Where things are like dynamics and everything.
Yeah.
Hypotheses about those environments are world models, right? Like that's
Yeah.
like hypotheses about environments are world models.
Yes.
So that's how I got into world models.
That's really cool. What do you think is driving like this interest in world models now? I know there's a bunch of folks at MIT working on it. I feel like probably a lot of papers, maybe I'm wrong, but I just got the impression it was sort of, like of interest. What do you think is driving that?
Well, I think we just kind of maybe like captured by this promise that like if you have like the right world model, then you're gonna be so sample efficient.
Okay.
Because then if you have like a good world model and you can plan in it, then you don't actually have to take actions in the real world, and then that's just gonna save a lot of like environment interactions, which could be very expensive.
Okay, that makes sense.
Yeah.
I thought it was going to be about just like it's an obvious thing that humans have that maybe our current AI doesn't have, and so it's like something's missing there.
I think for people who are like interested in like the cognitive science side of things, that's probably where they're coming from.
Yeah.
But I think for like more like robotics folk, they probably directly care more about like sample efficiency and all this kind of stuff.
Yeah.
But but now you have like both camp of people working on it, I think.
I'm so glad you took time to chat with us.
Yeah.
Maybe we could even do a longer form interview on POE World. I think it'd be really exciting to have you.
Yeah, that would be fun.
What are you looking forward to the rest of your NeurIPS 2025?
Honestly, just connecting with people. I think there are a lot of cool people here. A lot of people from India too,
Yeah.
right? You guys are very cool. I had a chat with Clem
Yes.
from India, and he was very fun too.
Yeah.
So I think it's about the people.
Yeah.
Yeah.
Well, thank you so much for taking time. I really appreciate it.
Thank you so much, Brian.
Here we are at a poster presentation at NeurIPS 2025 with an author here. Can you please introduce yourself?
Yeah, I'm Jumyong Park from GIST, and my primary interest is program induction with some more geometric approaches. And I'm actually an undergrad researcher, and so I'm looking for opportunities.
Why do you have a Rubik's Cube in your hand? I'm so curious.
Because that's related to what we have actually.
This is your
worked
poster
on.
right
Yeah.
behind us, right?
Yeah.
What do Rubik's Cubes have to do with your paper?
Because Rubik's Cube actually provides a very interesting playground of program synthesis. So it composed of various primitive approach, and if you can compose the actions, but what they span in the program space is non-trivial, but also that is heavily studied in the mathematics field as group theory. But also we have human solvers so that we can compare with how humans solve.
Are these human solvers like world record? Those people who can do it with one hand and everything.
Yeah, but
Yeah.
the interesting part is we also have various difficulty of human solving strategies. So
Yeah.
beginner's method and
Yes.
advanced method.
I bet there's a big variation
Yeah.
there.
So I think that provides some interesting playground that we can evaluate our methods on program synthesis.
I'm so curious. How did you make that connection? Were you playing with a Rubik's Cube and you were working on program synthesis and then had that insight? Like, where did that come from, that
Yeah.
idea?
Program synthesis and Rubik's Cube, they were all of my obsessions from the start.
That's so cool.
But also, what inspired me at the first place was the ARC, so abstraction and reasoning corpus. And I noticed that, this is a very generic framework where you can just substitute any input-output objects, where it forms a very complex yet interesting compositional structure, which is also more emphasized on ArcAGI 2. So I thought it might be a more easier and more nutritious playground
Yeah.
for especially these early stage researches.
That's so cool. Okay, what is the name of your paper so people can check it out?
Yeah, so our paper is composed program induction with latent program lattices.
Yep.
So we think that latent program lattice might provide a unifying framework for dealing with compositional reasoning.
That is so cool. Do you think you're going to keep kind of pulling the thread of program synthesis, or are you going to get pulled into the world of LLMs and never come back to the symbolic side?
It's very tempting to currently move on to LLMs because there's all the hype and interesting stuffs. And honestly, I also believe that they will also have more progress on these kind of discrete reasoning stuff. But also I'm quite aligned with the thought that we might have left this more symbolic part too early because of the early success of current scaling methods. So I actually want to devote more of my time on this more symbolic approaches and also the bridges between this neuro and symbolic part.
Yeah. Have you noticed anyone else? Like it does feel like there's a lot less representation of program synthesis here at NeurIPS this year. Does that seem true to you too?
I think they are all disguised in other names.
Yeah.
Also, I saw many interesting posters also in medical domains
Yes.
or also interpretability of current LLMs.
Nice.
I think there are more interest in how to represent or interpret the emergent behavior of the complexity and how could they even possible to do something remotely like reasoning.
Yeah.
So I think there's also more interest in that.
Yes.
And people are noticing that maybe there might be some structure and there could be something more than the bitter lesson.
Yes, for sure. Well, thank you so much. We're going to link to your paper in the show notes, and I hope everyone goes and reads it. Thank you for chatting with us.
Okay, thank you.
My name's Coco, Colin Conwell. I'm a hybrid academic industry researcher at MIT, working broadly in the space of computational cognitive neuroscience and also applications to program synthesis and other domains.
What is your paper about that you're presenting here?
So here we're presenting some work where we're trying to understand why deep neural network models can be more or less predictive of downstream brain activity. This is a kind of popular subfield where we're trying to understand properties of representation and computation in the brain by proxy models in the form of deep neural networks. And we're taking some fancy methods from things like statistical physics, a new emergent subfield called neural manifold geometry, to try and get a better sense of really what's going on when a brain model, like a deep neural network, predicts downstream brain activity.
This is amazing, Colin. You cover a lot of ground. I got to go back to the program synthesis stuff, though, because that's the focus of
Let's do it.
the India podcast. What do you think is exciting about program synthesis? This is an idea that's been around since, the 50s. It's not new stuff, but there are new opportunities with, in conjunction with deep learning, which you are an expert at. What do you think is cool about program synthesis?
So I think one of the fundamental premises of program synthesis is that we have a verifiable, executable method of doing something like computing the underlying functions that occur in things like deep neural networks, brains, and in behavior as well. Whether you're interested in the brain, the mind, or the body more generally, there's a sense in which we can map the things that we do to functions. Functions in terms are programs, and program synthesis is a way of thinking about, well, how can I use the understanding of programming languages to get a better grasp on, what's going on in the computations in the mind or in the body or in the brain. And so I think it's a really exciting time right now because basically a pseudonym for program synthesis is code generation.
Yes.
And so within the larger space of LLMs, one of the most exciting things to happen is that we have models now into which natural language can go and out of which programming languages come.
I have a question. Is this idea of kind of like the cognitive science angle of thinking of it as programs like a hot take? Is that like a controversial idea, or is this like a well-believed kind of?
No, not at all. In fact, one of the sort of seminal ideas of cognitive science was that there was a direct link to computer science. And in fact, that the original AI was in some form good old-fashioned AI, it used to be called, was the idea that we could, in fact, synthesize programs that would mimic aspects of the mind and brain. So this is basically one of the founding principles of cognitive science writ large. One of the sort of seminal moments, and I'm going to get the exact dates wrong, but was, I think, this thing called the Dartmouth Conference in the 60s, where Dartmouth, New Hampshire, where a bunch of folks got together, and it was in the early days of, computing. The MLP had kind of just a decade before been invented. So the perceptron was one of the first models, the neural module that instantiated how we could take something like neural computation and put it in a machine.
Wow.
And so there was this idea, well, actually we can kind of use the principles of computer science to model aspects of the mind and brain. And so it's a very canonical idea and deeply embedded. And in fact, it's if you yoke yourself to that particular path, you'll be very strongly in the traditions of cognitive science.
This is so cool. All right. So if you needed any interesting angles, even with program synthesis, but also sort of cognitive science meets machine learning, deep learning, all that is in here.
And also it links you directly to industry because major industry players like Google DeepMind have produced evolutionary program synthesis algorithms. AlphaEvolve is one instantiation of this, and another, in fact, done by neuroscientists at DeepMind, which is an extension of AlphaEvolve, is something called CogFunSearch. What's CogFunSearch? It's program synthesis for the purpose of creating functions that map onto brains and behaviors.
Got it. Thank you so much for your time.
My
Hope
pleasure.
you enjoy the rest of your NeurIPS.
Cheers. Thanks so much.
I'm Chris Hamblin. I've been working on ARC with this company Afterthought for about like 18 months now. But I started when I finished my PhD. I was in the Harvard Vision Sciences lab, and I worked on like computer vision interpretability.
That's exciting.
Yeah, which is different, but I actually think relevant, and a different version of maybe thinking about program synthesis than people conventionally think about it.
Okay, I want to dig in here. So how are you thinking of it? There's a sort of a classical definition of program synthesis.
Sure.
And now with, combined with deep learning and LLMs at this hyper scale, like there's all kinds of new approaches happening. Is that kind of getting at like what you're thinking in terms of?
Yeah, so I'm definitely not coming from like let's call classical program synthesis. You have some programming language and you have some specification of what you want a program to do, and you're doing some search process to find a program in this like large combinatorial space of things in the language. For me, I think one of the big problems with classical program synthesis is that you either have a pretty complicated language that's pretty flexible, Python, and you kind of like need an LLM or something, like it's too rich, or you have a DSL that's very specific.
Yes.
So then you also kind of have these questions of like where these programming languages even come from in the first place. So another way to think about it for me is that just training neural networks is already a version of program synthesis.
Tell me more.
It's like a very messy version.
Okay.
So
okay.
Coming from interpretability, what you're kind of trying to do is say, at the lowest level of description, you have this huge bag of weight matrices and it's super high dimensional and it's very complicated and who knows what's going on. So you have a very high level description of like the objective that you want to satisfy, and this very low level description that is amenable to anything because it's some universal function approximator. You could imagine that really there's like some virtual mesoscale description, kind of like maybe how like this term like phenomenology in physics. So there'll be these like statistical physicists and they'll say, well, really at the lowest level, there's just these molecules bouncing around and that's all that's going on, and there's simple rules, but in the sort of statistical chaos of it, you get these emergent phenomena that are very robust, that aren't noisy, like they're really real rules, like the ideal gas law.
Ooh, okay.
And they emerge from the low-level thing, from this process. And I think that's what happens in a lot of the training of neural networks. Like if you're doing computer vision interpretability, you're saying, we train to do ImageNet classification or something, but there is an algorithm that the model learns to do these things. There's something there and you have to figure out what it is. And I think working on ARC for me, it's more been like, okay, rather than just sort of post hoc interpreting models, how do you coax them and regularize them in such a way to encourage them to have like very compressed, nice representations so they look more algorithmic, so they don't so they memorize data less. But the hope being like, no, like it's possible. The optimizer is the search algorithm, a la program synthesis.
Yes.
I'm not coming from classical program synthesis.
Yeah.
And I don't want there to have to be a DSL.
Yeah.
Because then where did those come from?
I feel like you're being inspired by the concepts of program synthesis, and you're able to kind of squint and see, this order within the chaos of.
Well, I think they're just like they're isomorphic things. Like, what is a neural network? It's just like it's implemented on your computer.
Yeah.
It's a really big binary circuit. Right?
Sure.
And then there's all these levels of abstraction.
Do you have any sort of advice for people, based on your experience so far, where they might check out and steal ideas from that sort of symbolic side of AI?
Yeah, I mean, again, I don't think this is the only thing you can do. I think a lot of things could work and are interesting and maybe just related to each other and they're just under different guises. But I'm coming from this mechanistic interpretability world. There's big workshops for it here. And they really try to, they look at these neural networks post hoc and they figure out pretty precise algorithms about how they do different operations. If you think about a language model, something like, for example, just like syntax.
Yep.
Like that's a generative grammar. This is classic symbolic symbol manipulation stuff. They're perfect on grammar. They don't make grammatical errors. Right. So there's some formal process that they have internalized.
Sure.
But we don't know how they did it. So people go in post hoc and try to figure out what they're doing.
All right. Well, thank you so much for taking time out of your busy NeurIPS schedule. Hope you have a great rest of the conference.
Sure. You as well.